Right now, China's Tianwen-1 Mars probe is observing a jet structure extending 4 million kilometers from 3I Atlas, appearing in irregular directions that contradict standard solar-wind interactions, leaving scientists unsettled. Images captured on November 9, 2025, from Martian orbit show something that should not exist in this form, what some observers describe as an ion tail. Except the jets fire in patterns no simple comet has ever displayed. This is not how interstellar visitors are supposed to behave when the sun strips their surface away. The object was supposed to lose its tail. After passing within 37 million kilometers of the Sun on October 13th, it should have evaporated billions of tons of material into space, at least 13% of its total mass, according to standard sublimation models. Post-perihelion images from November 5th showed no clear cometary tail. Then came the acceleration. Between November 5 and November 10th, the object brightened faster than thermal models predict and shifted to a bluish hue, marking what observers are calling its third potential color change since detection. That spectrum does not match water ice. It does not match silicate dust. The signature points toward carbon dioxide ice, exotic ices, possibly irradiated by solar radiation in ways that remain poorly understood. Harvard astrophysicist Avi Loeb noted in his November 9th blog post that the absence of debris could mean the object fractured near the Sun, but updated tracking data confirms it remains intact. The jets remain active. The acceleration continues. Here's where it gets interesting. No standard comet model explains this combination of behaviors. Water ice comets outgas symmetrically when heated, producing predictable tails aligned with solar wind pressure. Carbon monoxide or carbon dioxide ice sublimates at different temperatures, yes, but the brightness curve for 3I Atlas climbed steeper than CO or CO2 alone can account for. Non-gravitational acceleration, the tiny push comets experience when jets fire asymmetrically, is measurable in this object. That push is stronger than the visible outgassing suggests it should be. Either there are hidden vents on the night side, or the internal structure is doing something unexpected. Engineers and planetologists are now circulating a hypothesis that months ago would have been dismissed outright. What if this is not a comet at all, but a fragment of a destroyed exoplanet, a shard of rock and ice ejected from another star system 7.5 billion years ago? Stop and consider that. The Sun is 4.6 billion years old. If the preliminary age estimate for 3I Atlas holds, this object formed 3 billion years before our solar system existed. It would be a geological time capsule from the epoch when the Milky Way was still assembling its spiral arms, when heavy elements were scarcer, when protoplanetary disks around distant stars were building worlds we will never see. The hypothesis is speculative, but it is not baseless. Spectroscopic data indicate carbon dioxide composition formed beyond the snowline, the boundary in a protoplanetary disk where temperatures drop low enough for volatiles to freeze. In our solar system, that line sits near Jupiter's orbit. In a hotter or more metal-poor system, it could lie farther out, baking different chemistry into the ice. If 3I Atlas is a planetary fragment, it would carry the mineralogy, the isotopic ratios, the frozen chemical fingerprints of an alien world that no longer exists. NASA planetologist Emily Saunders framed it this way. This is like deciphering a fragment from another star system where chemical and physical conditions radically differed from ours. She was careful to say like, not is. The scientific community has not endorsed the exoplanet hypothesis. Most astronomers attribute the unusual behavior to natural quirks, viewing angle effects, hidden sublimation, layered volatiles that release gas in pulses rather than steady streams. But the coincidences are stacking up. The object's trajectory lies close to the ecliptic plane, the flat disk where planets orbit the Sun. That is unusual for interstellar objects, which typically plunge through the solar system at steep angles because they come from random directions in the galaxy. The color shifts, green to blue, suggest surface chemistry responding to solar heating in stages, possibly indicating compositional layers. Think about what that means. Layers imply structure. Structure implies formation history. Formation history implies a parent body large enough and geologically active enough to sort materials by density and temperature, exactly the kind of differentiation that happens inside planets, not in the rubble piles that become comets. Here's the problem. If 3I Atlas is a planetary shard, where is the planet? Gravitational simulations show that rocky planets can be ejected from their home systems through close encounters with gas giants or during stellar flybys when a star passes near a planetary system and scrambles the orbits. Ejection velocities can reach hundreds of kilometers per second, enough to fling debris into interstellar space. Once free, the fragment drifts. 7.5 billion years is long enough to cross significant stretches of the galaxy, riding the slow currents of stellar motion. But here is the uncomfortable part. If ejection was violent, if a gas giant tore the planet apart, or a stellar encounter shattered it, there should be more fragments. 3I Atlas should not be alone. The galaxy should be littered with planetary debris from that event, and statistically, we should have seen others by now. We have not. Interstellar visitors are rare. 1I Oumuamua in 2017, 2I Borisov in 2019, now 3I Atlas in 2025, 3 objects in 8 years. If planetary destruction events seed the galaxy with fragments, either those events are far rarer than models suggest, or the fragments are so small and dark that our surveys miss them. Now about the data. The Tianwen-1 images show jet activity extending 4 million kilometers from the nucleus. To grasp that scale, the distance from Earth to the Moon is roughly 384,000 kilometers. The jets from 3I Atlas stretch more than 10 times farther. Ion tails, driven by the solar wind's magnetic pressure on charged particles, can grow enormous, but they point directly away from the Sun. These jets do not. Multiple ground-based observatories and Mars orbiters confirm irregular directionality, as though gas is escaping from discrete vents rather than a uniform evaporating surface. Avi Loeb suggested in his November 9th post that the pattern could resemble propulsion mechanisms or navigational aids in a hypothetical spacecraft. He immediately clarified this is speculative and almost certainly natural, but the phrasing ignited fresh debate. Loeb has history with controversial claims, having argued that Oumuamua might have been an alien light sail. The scientific mainstream rejected that interpretation, favoring nitrogen ice or hydrogen ice hypotheses. But Loeb's willingness to explore unconventional ideas has kept attention on these objects, and his analysis of 3I Atlas polarimetric properties, how light scatters off its surface, suggests the material is not standard cometary dust. Polarimetry measures the orientation of light waves after they bounce off a surface. Smooth, icy grains produce one signature. Rough, rocky grains produce another. Layered materials, especially those altered by heat and pressure over geological time, produce complex signatures that shift with viewing angle. Laboratory comparisons show that the polarimetric curve of 3I Atlas resembles certain terrestrial rocks subjected to diagenesis, the low-grade metamorphism that cements sediments into stone and recrystallizes minerals without melting them. Diagenesis requires time, pressure, and often liquid water or hydrothermal fluids. If the surface of 3I Atlas shows diagenetic alteration, it would support the hypothesis that this object once sat inside a geologically active body, buried under kilometers of overburden, slowly transforming under the weight of a planet that no longer exists. Here's where things get strange. The object lost no mass in the expected way, but it accelerated. Non-gravitational forces pushed it off a purely gravitational orbit. The magnitude of that push, measured by comparing predicted position to observed position, implies outgassing equivalent to several tons per second of material. Observers see jets, yes, but not enough visible dust or gas to account for the acceleration. Hidden vents could explain it. If the sun heats one hemisphere while the object rotates, subsurface ice could vaporize and escape through cracks on the night side, invisible to telescopes pointed at the day side. Alternatively, the nucleus could be spinning in a way that focuses jets into narrow beams we only glimpse intermittently. Both scenarios require fine-tuned geometry, and both rely on assumptions about the rotation state that have not been confirmed. The object is small, likely no more than a few hundred meters across, possibly smaller. At that size, even powerful telescopes cannot resolve surface features, only the surrounding cloud of gas and dust. Direct imaging of the nucleus will not happen until it passes closer to Earth or a spacecraft intercepts it, neither of which is currently planned. The December 19, 2025 flyby offers a narrow window. At closest approach, 3I Atlas will pass 270 million kilometers from Earth. That is beyond Mars' orbit, nearly twice the distance to the Sun, far, but not impossibly far for infrared and radio telescopes. The James Webb Space Telescope can observe faint objects at that range, and astronomers have submitted proposals to scan the object's thermal emission, searching for temperature variations that would reveal surface composition and outgassing patterns. Webb's spectrometers can detect carbon dioxide, carbon monoxide, methane, water vapor, silicate dust, organic molecules, anything that emits or absorbs infrared light. If the surface is layered, if diagenesis occurred, if exotic ices are present, Webb will see them. Ground-based radio arrays can measure the object's rotation by tracking Doppler shifts in gas emission lines, revealing whether it tumbles chaotically or spins steadily, a clue to its structural integrity. A rubble pile tumbles. A solid fragment spins predictably. Read between the lines. NASA has not released high-resolution images from the Hubble Space Telescope or the Mars Reconnaissance Orbiter, both of which have the capability to observe 3I Atlas in detail. Hubble tracked the object in early November, and MRO has instruments sensitive to ultraviolet and visible wavelengths that could reveal surface features invisible to ground telescopes. The absence of published data is not necessarily suspicious. Scientific imaging pipelines take time, and peer review delays publication, but the silence has fueled speculation. Some observers wonder whether preliminary findings are ambiguous enough that agencies prefer to wait for confirmation before issuing statements. Others suggest the images show nothing unusual, and the delay reflects standard procedural caution. Either way, the gap between observation and publication creates uncertainty, and uncertainty creates space for hypotheses to flourish. The exoplanet fragment hypothesis rests on several pillars. First, the age estimate, 7.5 billion years, derived from assumptions about the object's trajectory through the galaxy and the decay of surface features under cosmic ray bombardment. Cosmic rays, high-energy particles that pervade interstellar space, gradually sputter away surface atoms, eroding exposed rock and ice. Measuring the depth of radiation damage requires either a sample return mission or detailed spectroscopy of surface minerals, neither of which is feasible yet. The age estimate is therefore indirect, inferred from the object's velocity relative to nearby stars and the statistical likelihood of certain galactic orbits. It is a model, not a measurement, and models have uncertainties. Second, the chemical composition. Carbon dioxide ice formed beyond the snow line. That is consistent with planetary formation, but it is also consistent with Kuiper belt objects, Oort cloud comets, and rogue planetesimals. Carbon dioxide is common in the outer regions of any protoplanetary disk. Finding it on 3I Atlas does not prove planetary origin, only that the object formed in a cold environment. Third, the structural integrity, the absence of fragmentation despite close solar approach. Rocky asteroids survive, close sun passes routinely, so durability alone does not distinguish a planetary shard from a solid interstellar asteroid. What distinguishes this object is the combination age plus composition plus trajectory plus polarimetry plus non-gravitational acceleration plus irregular jets. Each piece is ambiguous. Together, they form a pattern that does not fit standard templates. Emily Saunders emphasized the diagnostic potential of isotopic ratios. On Earth, the ratio of oxygen-16 to oxygen-18, or carbon-12 to carbon-13, varies slightly between different reservoirs, ocean water versus atmospheric carbon dioxide versus limestone, because chemical and physical processes preferentially sort isotopes by mass. Planets do the same. A fragment from an exoplanet would carry isotopic signatures reflecting the composition of its parent star's protoplanetary disk, which depends on the star's metallicity, the abundance of elements heavier than helium. If the parent star was metal-poor, an ancient population 2 star formed early in galactic history, its disk would have less silicon, iron, and oxygen than our Sun's disk, and minerals formed in that disk would show depleted heavy isotopes. If the parent star was metal-rich, a young population 1 star like the Sun, isotopic ratios might resemble solar system materials, making planetary origin harder to prove. Measuring isotopes in a fast-moving interstellar object requires high-resolution spectroscopy, observing the precise wavelengths of emission or absorption lines from molecules like carbon monoxide or water vapor, and extracting isotopic shifts that are often smaller than the instrument's resolution limit. The James Webb Space Telescope has the sensitivity, but only if the object outgasses enough molecules to produce detectable lines. If the nucleus is mostly rock with a thin ice veneer, if outgassing drops as it moves away from the Sun, the signal will fade before Webb can accumulate sufficient data. Think about what that means for mission planning. The December flyby is not optimal. The object will be receding from the Sun, cooling, outgassing less. Peak activity occurred in October during perihelion. Observations then would have been ideal, but 3I Atlas was only confirmed as interstellar in late September, too late to mobilize major observatories or redirect spacecraft. The discovery itself was delayed because the object approached from the direction of the Sun, invisible against the glare, until it swung past and emerged into the pre-dawn sky. By the time astronomers recognized its interstellar origin, the best observing window had partially closed. The March 16, 2026 flyby past Jupiter offers another opportunity, but the object will be even farther from the Sun, colder, less active. Jupiter's gravity will bend the trajectory slightly, potentially revealing more about the object's mass if precise astrometry tracks the deflection, but gravitational microlensing is subtle and requires careful measurement. After Jupiter, 3I Atlas will climb out of the inner solar system, accelerating toward interstellar space, fading beyond the reach of all but the most powerful radio telescopes. This is a closing window. Scientists face a decision tree. If 3I Atlas is a comet, a dark Kuiper belt object kicked out of another star system by gravitational scattering, then its behavior, while unusual, falls within known physics. Carbon dioxide outgassing, layered volatiles, hidden vents, all plausible, all observed in solar system comets under various conditions. If it is a planetary fragment, the implications cascade. It would mean planets are destroyed and ejected often enough that fragments occasionally cross paths with our solar system. It would mean interstellar space is not empty, but seeded with the wreckage of dead worlds. It would mean we can study exoplanetary geology without traveling light years, because the galaxy delivers samples to us. It would reframe the search for biosignatures. If a fragment retains organic molecules, amino acids, or even fossil microbes from a long-dead ocean, and if those molecules survive 7 billion years of radiation and cold, then interstellar objects become archives of extinct biospheres. The probability is low. Preservation over such timescales requires extraordinary conditions, but low is not zero. Avi Loeb has argued that the scientific community dismisses unconventional hypotheses too quickly, clinging to the principle that extraordinary claims require extraordinary evidence while refusing to gather that evidence. His critics counter that resources are finite, telescope time is precious, and chasing long-shot ideas diverts effort from productive research. The tension is real. Interstellar objects appear rarely, perhaps one every few years, and each passage is brief. Comprehensive study requires rapid response, coordinated international effort, dedicated funding. None of that infrastructure exists. When Oumuamua vanished in 2017, astronomers vowed to prepare better for the next visitor. When 2I Borisov appeared in 2019, observations improved, multiple telescopes tracked it, spectra were obtained, but the object turned out to be a fairly ordinary comet, chemically similar to solar system comets, offering no revolutionary insights. Now, 3I Atlas presents a third chance, and the preliminary data are strange enough to justify intense scrutiny, but strange is not synonymous with artificial or even exotic. Strange often means undersampled, poorly understood, or statistically unlikely, but still natural. The propulsion mechanism language that Loeb used, even hedged with disclaimers, triggered predictable backlash. Mainstream astronomers accuse him of conflating natural phenomena with techno-signatures, of seeking attention rather than truth. Loeb responds that science advances by testing bold ideas, not by ruling them out prematurely. The debate has become personal, which is unfortunate, because it obscures the legitimate scientific question. What physical processes can produce the observed combination of properties in 3I Atlas? If the answer is unknown, then the object is genuinely anomalous, and anomalies drive progress. If the answer is known but rare, then the object is a statistical outlier, interesting but not paradigm-shifting. If the answer is we lack the data to decide, then the imperative is to gather more data, not to argue about interpretation. The greenish glow observed in early November, before the blue shift, is diagnostic of diatomic carbon, C2, a molecule that fluoresces green when excited by sunlight. Diatomic carbon is common in comets, produced when organic molecules break apart under ultraviolet radiation. Its presence confirms that 3I Atlas contains carbon-rich material, but the intensity of the glow was unusually strong, suggesting either high carbon abundance or efficient fluorescence, possibly due to surface texture or dust grain size. The subsequent shift to blue, if confirmed by multiple independent observations, implies a change in surface composition or temperature. Blue in comets often correlates with ionized carbon monoxide, CO+, which emits in the blue and ultraviolet when stripped of an electron by solar wind. The transition from green to blue could indicate that C2 dominated during the initial outburst, then depleted as the more volatile CO sublimated and ionized. Alternatively, viewing geometry might have changed, altering which part of the coma was visible. Without continuous monitoring, distinguishing between intrinsic evolution and observational artifact is difficult. The trajectory analysis adds another layer. Interstellar objects have hyperbolic orbits, meaning they move faster than escape velocity and will never return. The shape of the orbit, specifically the eccentricity and inclination, encodes information about the object's velocity at infinity, the speed it had in interstellar space before the Sun's gravity bent its path. For 3I Atlas, the velocity at infinity is estimated at roughly 26 kilometers per second relative to the local standard of rest, the average motion of stars in the Sun's neighborhood. That is modest. Oumuamua had a similar velocity, while 2I Borisov was faster, around 32 kilometers per second. Lower velocity suggests the object originated from a nearby star, one within a few dozen light years, or that it has been wandering the galaxy for a long time, gradually losing speed through distant gravitational interactions with passing stars. If the object is 7.5 billion years old, it has had ample time to slow down, making the modest velocity consistent with ancient origin. However, tracing the trajectory backward to identify a plausible source star is nearly impossible over such timescales. Stellar positions change as stars orbit the galaxy, and small uncertainties in velocity compound exponentially over billions of years. The best astronomers can do is rule out recent ejection from nearby systems. The irregular jet directions invite mechanical explanations. If the nucleus is elongated, tumbling chaotically, jets could fire from multiple vents at different latitudes and longitudes, creating an asymmetric coma that shifts appearance as the object rotates. If the surface has cliffs, craters, or fractures, sunlight could concentrate heat in topographic hollows, triggering localized outbursts. If the interior is layered with pockets of different ices, carbon dioxide here, methane there, water deeper down, then sequential sublimation as heat penetrates inward could produce time-variable activity. All of these mechanisms are observed in solar system comets. Comet 67P Churyumov-Gerasimenko, visited by the Rosetta spacecraft, displayed jets from discrete sources, neck regions where two lobes met, cliffs where fresh ice was exposed. Comet Hale-Bopp in 1997 showed a complex coma with multiple tails, dust tails, ion tails, sodium tails, each responding to different forces. The challenge with 3I Atlas is that we cannot see the nucleus, cannot map the surface, cannot confirm which mechanisms operate. Analogies to solar system comets are useful but not conclusive. The absence of debris is harder to explain. When comets fragment, they leave trails of smaller pieces that gradually spread along the orbit, creating meteor streams if they intersect Earth's path. 3I Atlas shows no such trail. Telescopic surveys designed to detect faint moving objects have searched the vicinity and found nothing. That suggests either the nucleus is structurally intact, held together by tensile strength strong enough to resist tidal stress and thermal shock, or it fragmented recently and the pieces are too small and faint to detect. Strength depends on composition. Ice alone is weak, fracturing easily under stress. Rock is stronger, but interstellar objects are cold, and cold rock can be brittle. Mixtures of ice and rock, if intimately bonded, can be surprisingly tough, as seen in some carbonaceous chondrite meteorites, which are porous yet coherent. If 3I Atlas is a planetary fragment, it might consist of material that underwent lithification, the process by which loose sediment becomes solid rock, either through burial and pressure or through aqueous alteration in a subsurface ocean. Lithified material would resist fragmentation better than a loosely bound rubble pile. The hypothesis that 3I Atlas could be a key to understanding ancient exoplanetary systems hinges on whether we can extract meaningful data before it leaves. The James Webb Space Telescope is the best tool available, but it is oversubscribed, with observing time allocated years in advance for hundreds of approved programs. Emergency target of opportunity slots exist for transient events, supernovae, gamma-ray bursts, and potentially interstellar objects, but claiming those slots requires compelling justification. Astronomers must convince a review panel that the object is unique, that the science return outweighs the disruption to scheduled observations, and that the data cannot be obtained any other way. Preliminary results showing ambiguous spectra or inconclusive morphology might not meet the threshold. Extraordinary evidence is needed to unlock extraordinary resources, creating a paradox. The evidence requires the resources, but the resources require the evidence. Ground-based observatories face fewer bureaucratic hurdles, but have physical limits. Atmospheric turbulence blurs images, weather interrupts observations, and thermal emission from Earth's atmosphere drowns out faint infrared signals. Adaptive optics systems can partially correct turbulence, and high-altitude sites like Mauna Kea or the Atacama Desert minimize atmospheric interference, but 3I Atlas is faint and will grow fainter as it recedes. Large arrays like the Atacama Large Millimeter Array, ALMA, can detect molecular emission with exquisite sensitivity, mapping the distribution of carbon monoxide, methanol, or formaldehyde in the coma, molecules that trace the object's chemistry. ALMA has observed comets before, revealing complex organic inventories, but those were bright, nearby comets. Whether ALMA can detect a faint interstellar object at hundreds of millions of kilometers is uncertain without trying. Radio telescopes offer another avenue. If the object outgases water or hydroxyl radicals, OH, those molecules emit at specific radio frequencies, 18 centimeters for OH, a wavelength accessible to large single-dish telescopes like Arecibo, now lost, or Green Bank, still operational. The Very Large Array in New Mexico can observe in multiple wavelengths simultaneously, tracking both thermal emission from dust and line emission from molecules. Radio observations are immune to daylight and weather, allowing round-the-clock monitoring, but they require that the target emits strongly enough to stand out against background noise. Comets near the Sun are bright radio sources. Comets far from the Sun are often silent. The question is whether 3I Atlas retains enough activity in December to remain detectable. The color changes, green to blue, now potentially shifting again, suggest dynamic surface processes. Each color corresponds to different molecules or ions, and their abundance depends on temperature, solar irradiation, and the availability of parent molecules in the ice. If the object is warming up as it moves away from the Sun, that is counterintuitive, but possible if delayed heat release occurs, subsurface layers vaporizing after absorbing heat during perihelion and conducting it inward. Some comets brighten post-perihelion for this reason. If 3I Atlas is cooling, then the color changes reflect depletion of volatiles, the most reactive molecules escaping first, leaving behind more refractory material. Tracking color evolution over weeks and months maps the chemical stratification of the nucleus, like reading the layers of a geological core sample, except the layers are revealed by sequential sublimation rather than drilling. Avi Loeb's polarimetric analysis remains controversial but intriguing. Polarimetry is underutilized in asteroid and comet studies because it requires specialized instruments and careful calibration, but it is sensitive to surface microstructure in ways that photometry and spectroscopy are not. If the polarimetric curve of 3I Atlas truly resembles diagenetically altered rock, and if that resemblance holds up under independent verification, it would be the strongest single piece of evidence for planetary origin. Diagenesis is a planetary scale process. It does not happen in small, cold, isolated bodies. It requires burial, time, and often fluids. Detecting its signature on an interstellar object would imply a parent body at least hundreds of kilometers across, large enough to have internal heat, possibly large enough to differentiate into core, mantle, and crust. Such a body would be a dwarf planet, or small planet, not a comet or asteroid in the conventional sense. The implications for astrobiology are speculative but worth considering. If planets form around most stars, and if some fraction of those planets develop oceans, atmospheres, and possibly life, then planetary destruction events scatter fragments into the galaxy, some carrying remnants of those biospheres. Organic molecules are fragile, radiation breaks them down, but certain molecules, polycyclic aromatic hydrocarbons, amino acids embedded in minerals, lipids trapped in rock pores, can survive harsh conditions for extended periods. Meteorites that fall to Earth contain amino acids formed in space, proving that complex organics persist in interplanetary environments. Whether they could survive interstellar transit over billions of years is unknown. No experiment has tested it, but thermodynamics allows it. If radiation exposure is limited, if the fragment is large enough that the interior remains shielded, if the temperature stays cold enough to inhibit chemical reactions, then preservation is possible. Finding such molecules on 3I Atlas would not prove life existed on its parent body. Organic chemistry is ubiquitous and mostly abiotic, but it would establish that fragments can carry complex chemistry across interstellar space, making panspermia, the transfer of life between star systems, marginally more plausible. The timeline pressures are acute. December 19th is 5 weeks away. Telescope proposals need days to weeks for review and approval. Instruments need time to calibrate. Observation plans need coordination across facilities and time zones. If the scientific community waits for peer-reviewed confirmation of the anomalies before acting, the object will have moved beyond optimal range. If they act prematurely, investing resources in an object that turns out to be mundane, the opportunity cost is real. Other science gets delayed. Other targets go unobserved. The decision must be made on incomplete information, a gamble that the preliminary data are reliable and that the payoff, understanding an ancient interstellar fragment, justifies the risk. NASA's silence on Hubble and Mars reconnaissance orbiter data complicates planning. If those images show clear morphology, jets, rotation, surface features, then targeting strategies can be optimized. If the images are ambiguous, showing only a faint smudge, then expectations must be tempered. The lack of public release could mean the data are still under analysis, embargoed until a paper is ready, or it could mean the data quality is poor, below the threshold for publication. Either way, astronomers working on observing proposals are operating partially blind, forced to assume the object is as interesting as preliminary reports suggest without confirmatory evidence. The broader scientific context matters. Interstellar objects are probes of galactic processes, sampling the diversity of planetary systems in ways that direct observation cannot yet achieve. Exoplanet surveys have found thousands of planets, but they are biased toward large planets close to their stars, hot Jupiters and super-Earths, because those are easiest to detect. Small, cold, distant planets, the kind that might be ejected and become interstellar wanderers, are mostly invisible to current telescopes. Interstellar objects provide the complementary sample, the leftovers, the ejecta, the failures. Studying them reveals what happens when planetary systems go wrong, when orbits destabilize, when collisions occur, when stars die or are disrupted. If ejection is common, as some models suggest, then billions of interstellar objects pass through the solar system every year, most too small and dark to detect. The few we do see are likely the tip of the distribution, the largest and brightest. Understanding their properties constrains the unseen population. The economic and political dimensions are present but understated. Space agencies operate on fixed budgets, and reallocating resources to study 3I Atlas means delaying or canceling other projects. Justifying the trade-off requires consensus that the object is worth it, and consensus is hard to achieve when data are ambiguous. International collaboration helps, sharing telescope time, pooling expertise, distributing the workload, but it also introduces coordination challenges and competing priorities. China's Tianwen-1 provided the November 9th images, a valuable contribution, but access to the full data set depends on whether Chinese space authorities release the raw data to international researchers. Similar considerations apply to NASA, ESA, and other agencies. Data sharing norms in astronomy are strong but not absolute, and sensitive or high-value observations are sometimes embargoed. The hypothesis that 3I Atlas is a planetary fragment is testable but not easily. Testing requires measuring isotopic ratios, mapping surface composition, determining structural integrity, and constraining the rotation state. Each measurement demands specific observations, some feasible with current technology, others requiring future missions. A sample return mission, the gold standard for planetary science, is impractical. The object is moving too fast and is too far for any existing or planned spacecraft to intercept. Remote sensing is the only option, and remote sensing has limits. Spectra reveal chemistry, but not context. Polarimetry reveals texture, but not history. Photometry reveals brightness, but not cause. Integrating all available data into a coherent model is the challenge, and models are always underdetermined when the data are sparse. The scientific process favors caution, multiple independent confirmations, peer review, replication. Those safeguards prevent errors but slow discovery. When the object of study is transient, moving, fading, caution costs opportunity. The balance is difficult. Rushing to conclusions undermines credibility. Waiting for certainty loses the chance to observe. The resolution is to proceed with observations while maintaining epistemic humility, gathering data without overinterpreting, publishing results with appropriate caveats, letting the evidence accumulate until the uncertainty narrows. That process takes time, months or years, but 3I Atlas will not wait. The March 16, 2026 Jupiter flyby adds a coda. Jupiter's immense gravity, 318 times Earth's mass, will bend the object's trajectory measurably, a natural test of its mass and density. If the deflection matches predictions for a low-density ice ball, a few hundred kilograms per cubic meter, then the comet interpretation strengthens. If the deflection is smaller, implying higher density, rock or metal rather than ice, then the planetary fragment hypothesis gains support. The measurement requires precise astrometry, comparing predicted position to observed position within arcseconds, challenging but achievable with dedicated tracking. Jupiter's magnetosphere might also interact with any outgassing, ionizing molecules and accelerating them into jets, potentially creating auroral emissions detectable in ultraviolet or radio wavelengths. NASA's Juno spacecraft, in orbit around Jupiter, might be able to observe the encounter, depending on orbital geometry and instrument pointing, adding another data source. The narrative arc of 3I Atlas, from discovery to perihelion to flyby to departure, mirrors the structure of scientific inquiry: detection, hypothesis formation, data collection, analysis, conclusion. We are in the middle phase, data collection, where the outcome remains uncertain. The object is visible, active, observable, but the observations are difficult and the interpretations contested. In the coming weeks, as telescopes track it and spectra accumulate, the uncertainty will narrow. Either the anomalies will resolve into known physics, exotic but natural, or they will deepen, forcing a re-evaluation of what interstellar objects can be. Either outcome advances knowledge. The worst outcome is ambiguity, data too poor to decide, leaving the question open and unanswered. If the exoplanet hypothesis is correct, if 3I Atlas is indeed a 7.5 billion-year-old shard of a destroyed world, then its passage through the solar system is a singular event. We have received a message from the ancient galaxy, not encoded in radio waves or laser pulses, but written in stone and ice, delivered by gravity and chance across distances and times that dwarf human comprehension. The message is not intentional. It carries no greeting, no warning, no wisdom. It is simply evidence, raw data, the residue of processes that occurred when the universe was younger and less predictable. Reading that message requires instruments and minds capable of deciphering signals degraded by time and space, of extracting meaning from fragments, of reconstructing a whole from a part. That is what science does. The countdown is running. December 19th approaches. Telescopes are being scheduled. Proposals are being written. Scientists are hedging their language, avoiding definitive claims while preparing for the possibility that this object might rewrite parts of planetary science. The public narrative, shaped by press releases and blog posts, oscillates between excitement and skepticism, between the hope that 3I Atlas is extraordinary and the expectation that it will prove ordinary. The tension sustains interest but also distorts perception, making it harder to communicate nuance. An object can be scientifically important without being revolutionary. It can be unusual without being unprecedented. The categories overlap but are not identical. The final question is not whether 3I Atlas is a planetary fragment. The final question is, what would it mean if it were? It would mean the galaxy is more violent than the serene images of spiral arms and star clusters suggest, that planetary systems are fragile, that worlds are born and destroyed in numbers we have not yet grasped. It would mean the space between stars is not empty, but filled with the wreckage of those worlds, silent, dark, waiting to be discovered. It would mean that understanding our place in the cosmos requires looking not just at the light of distant stars, but at the debris they cast off, the remnants, the outcasts. It would mean that the history of planets is written not only in the planets that survive, but in the fragments of those that did not. And it would mean that 3I Atlas, a small, cold, unremarkable-looking object passing through our solar system for a few months, is a key to that history, a cipher, a clue. If the data are correct, if the age estimate holds, if the composition and trajectory and polarimetry and acceleration all align, then how deep does this mystery go? How many other fragments drift through the galaxy, unseen and uncounted, carrying the secrets of extinct worlds? How often do planetary systems destroy themselves, and what does that imply for the stability of our own? If a fragment can carry organic molecules across billions of years and light-years of space, what else might it carry? And what might we learn by finding it? The questions spiral outward, each answer generating new questions, the hallmark of a genuine scientific frontier. 3I Atlas may be the first fragment we have recognized, but it will not be the last. The galaxy is vast, and we are just beginning to listen to what it has to say.